Hello everyone, welcome back to our TCE online course on marketing and social media web analytics. I am T. Shiva, Assistant Professor from Department of Computer Science and Business Systems at Tyagaraja College of Engineering. Today we are going to explore a fascinating concept called random graphs. These concepts may sound mathematical at first, but they are extremely important for understanding how social media networks grow, how viral concepts spread, how communities form, and how connections evolve even without any planning. By the end of this session, you will understand how randomness creates networks that looks but actually follows a beautiful mathematical pattern. So let's begin. So this is the progress of the course. In the last video, we have seen about the power of link analysis. Today we are going to see about random graph network born in chaos. In today's class, we will go step by step through the following topics. What are random graphs? The ER model, the two model graphs, that is G of NP and G of NM, key mathematical properties, examples and problem solving, applications in real systems, and quiz at the end of this particular session. So what are random graphs? A random graph is a network that is generated purely by chance. Nothing is planned. No structure is pre-designed. Imagine we have a group of nodes, maybe people in social platform, and we start connecting them randomly. Some people get many connections, but some people only one. They will get only one connection. Some get none. There are no pattern, no rule, just probability steering everything. Random graph helps us to understand the natural system by giving us a baseline model. We can compare real networks to the random one and understand what is happening because chance and what is happening because of real social or biological structure. ER model. It is created in 1959 by mathematician Paul Edros and Alfred Rhine. The ER model introduced two versions of random graphs. One is G of NP and G of NM. These two versions are backbone for everything we study in random network. G of NP model. In G of NP model, we first start with n nodes. For every possible pair of nodes, we decide whether to connect them using probability P. If P equal to 0.1, every edge has 10% chance of existing. Each edge is chosen independently. G of NM model. Here, instead of using probability, we simply say we want exactly m edges. So, randomly picking m edges from the total possible nodes and pairs. Why randomness in network? Randomness gives clean mathematical predictions, reveals emergent behavior, acts as a baseline, and helps us detect when real networks deviate from randomness. Probability driven edges. The total edges equal to n into n minus 1 by 2. Using this formula, we can calculate the total edges, and for calculating the expected edges, we can use the formula of P into n minus 1 divided by 2. Each edge appears independently. Degree distribution. The degree of a node is the number of edges connected to it. In ER network, the degree distribution follows a Poisson distribution. Average degree, that is lambda, equal to P into n minus 1. So let us see an example of a degree distribution. In this, the values of n is 1000, that is the number of nodes are 1000, and the edge probability is p equal to 0.01. To calculate the expected degree, we can use the formula E of k equal to n minus 1 into p. So we know the value of n is 1000, so n minus 1 is 999 into 0.1. So the expected degree will be approximately 10. Similarly, for calculating the degree variance, var of k equal to n minus 1 into p into 1 minus p. So by substituting these values, we can calculate the degree variance is also approximately 10. Clustering coefficient. Clustering coefficient P. ER networks have low clustering unlike real social networks, which shows strong tracked closure. Connectivity threshold. A giant connected component form when P equal to 1 by n. Below this, the graph is fragmented. Above this, it may be mostly connected. Giant component formation. Giant component is a large connected subgraph. Once P crosses 1 by n, a large connected component suddenly appears. Average path length. Average path length equal to, it can be calculated using the formula log of n divided by log of np. ER network exhibits short paths similar to small world behavior. So some real world applications. The ER model helps understanding communication networks, technological infrastructure, biological interactions, and many more. But still it has some limitations. So ER model lacks hubs, power law degree distribution, clustering and community structure, important feature of real social networks. So let's take a case study of social networks. It has random friendships, information spreading. If you take the case study of biological network, it is germ mutations and protein interaction. So let's solve few problems relevant to this particular topics. The first problem is relevant to edge probability. Let's walk through our first problem. We are given a random graph G of 50, 0.1. This tells us two things. N is equal to 50, there are 50 nodes, and P equal to 0.1, which is the probability of each degree. Now, here is a key idea. In G of NP model, the probability that any particular edge exists is exactly P. There are no condition, no formulas, nothing extra. So, in this case, the probability of specific edge exists is simply P equal to 0.1 or 10%. That's the entire logic. This helps us understand how randomness decides connections between nodes. So next problem is relevant to expected degree. For this problem, we have a G of 500, 0.02 graph. We want the expected degree of a node. The formula for expected degree in ER network is E of k equal to n minus 1 into p. So let's plug this value. E of k equal to 500 minus 1 into 0.02, which gives 499 into 0.02, which is equal to 9.98. So the expected degree is approximately 10. This means on average each node is connected to about 10 others. Notice how even with a small probability networks become fairly connected. Next problem is on connectivity threshold. This is one of the most beautiful results in random graph theory. The connectivity thresholds appear when P greater than or equal to In of n divided by n. So let's substitute In of 1000, which is approximately equal to 6.9075. So P greater than or equal to 6.9075 divided by 1000. So P greater than or equal to 0.0069. This means with just 0.69% probability per edge, the network suddenly become connected as a single chain component. This shows how little randomness is needed for a large scale connectivity. Next problem is relevant to expected number of edges. Now we are calculating expected edges, not degree. The formula for calculating the expected edges is P into n minus 1 divided by 2. Let's compute n into n minus 1 divided by 2. So 200 into 199 divided by 2. So the answer we will get is 19,900. Then expected edge equal to 0.05 into 19,900. So 995. So with a 5% edge probability, we expect around 995 edges. Next problem is about chain component check. To check if the chain component exists, we use the rule a chain component formula when NP greater than 1. Now calculate NP equal to 800 into 0.002, which is equal to 1.6. Since 1.6 is greater than 1, yes, the graph contains a chain component. This tells us even a small probability can link most nodes together. So we cover ER model basics, structure, properties, applications and limitations in this video. Now let us see few questions to check whether you have understand the concepts clearly or not. Let's go to our first question. The question asks, the ER model was proposed in which year? The options are 1945, 1959, 1968, 1975. And the correct answer is 1959. This was the year ER published the year groundbreaking papers. Our next question is about G of NM model. The question asks, what does the parameter M represents? The options are probability of an edge, number of nodes, a fixed number of edges, expected number of edges. And the answer is a fixed number of edges. G of NM literally means choose M random edges. Third question. What is the critical point of P at which a chain component appears? The options are P equal to log n, log of n, P equal to n divided by log of n, P equal to n, and P equal to 1 by n. So the answer is option D, P equal to n by n. This threshold marks the sudden emerge of chain cluster. The fourth question. The question is, ER networks are categorized by what? The options are high clustering, low clustering, power law degree distribution, many hubs. And the answer is low clustering. ER networks do not naturally produce triangles or group clusters. Fifth question. It's a final question. Which of the following is a major limitation of ER model? Option A, it simplifies modeling. Option B, it predicts emergent phenomena. Option C, it has short path lengths. Option D, it does not model hubs or power law distribution. The correct answer is it does not model hubs or power law distribution. This is why ER models do not match real social networks. So thank you for joining today's session on random graphs. The topics form foundation of modern network analytics. In the next class, we will explore more realistic network models that match social platform more closely. Until then, keep learning, stay curious, happy learning. So if you have any doubts, you can contact me at any time. Thank you.